Let's talk about something incredible, the high-stakes science of moving millions of barrels of oil across the ocean. Now, this isn't just a story about giant ships. It's about the invisible engineering, the complex web of systems where every single valve, every sensor is part of a safety net designed to prevent an absolute catastrophe.
To really get this, you have to appreciate the scale. We're talking about a single modern supertanker carrying 2 million barrels of crude oil. That is an almost unimaginable amount of energy. And of course, with that much energy comes an incredible amount of risk.
So, that brings us to the big question, right? The one that keeps naval architects up at night. How in the world do you keep this giant floating steel box filled with a highly flammable liquid from essentially becoming a bomb? Well, the answer is this beautiful symphony of preventative engineering.
But before we get to the solutions, we have to know what we're up against. These are the enemies, the constant threats that every single system on that ship is designed to defeat. You got the obvious ones like fire and spills, but then there are the sneakier dangers, structural failure from stress, toxic gases, or the whole vessel just becoming unstable. It's a constant battle against physics and chemistry.
Now, you might think the fight for safety begins when the oil starts pumping, but nope, it starts way before that, in the planning phase. Before even a single drop of cargo gets loaded, this incredibly intricate digital plan is created to make sure the ship stays perfectly balanced and stress-free for the entire voyage.
At the heart of all this planning is something called the stowage plan. You can think of it as the master blueprint for the trip. It dictates exactly which tanks get filled, in what order, and with how much oil. And it's not just about weight, it's about making sure the massive forces acting on the ship's hull are distributed perfectly.
And the tool that makes all this possible? It's called the Loadicator. I love this description. It's basically the ship's digital conscience. It's a specialized computer that takes that stowage plan and just runs thousands of calculations, checking for stability and stress in real time. This is the brain of the operation, verifying every single decision against razor-thin safety margins.
Okay, so the plan is set. It's been verified. Now it's time for action. And let me tell you, loading an oil tanker is nothing like filling up your car. It is a high-stakes, perfectly controlled flood where multiple overlapping safety systems are all working at once to manage insane pressures and flammable vapors.
The whole process is incredibly methodical. First, the crew sets up this massive network of pipes and valves, the ship's arteries, really. Then they connect a system to capture all those flammable gases. The loading starts off slow, and that's key to prevent static electricity from building up. And the whole time, every vital sign, pressure, flow rate, you name it, is being watched constantly. The final stage, called topping off, is done at a crawl, just to make sure there's zero chance of an overfill. Because really, the two biggest nightmares during this phase are 1, a spill from overfilling a tank, and 2, an explosion from the vapors that get pushed out as the oil goes in. Pretty much every safety system we're about to talk about is designed to prevent one of those two things from happening.
The defense system here is layered. First up, you've got the high-level alarm. Think of this as the yellow light. It goes off when a tank is about 95% full, basically telling the operator, hey, time to slow down. But if for some reason that warning is missed, the overfill alarm kicks in. This is the red light, the emergency brake. At 98%, it doesn't just make a noise. It automatically, instantly shuts down all the valves and stops the flow. Period.
But wait, slamming a valve shut on millions of barrels of flowing liquid creates its own massive problem, a pressure surge. You might have heard of this as water hammer in the pipes in your house. Well, on a tanker, that shockwave is powerful enough to literally rupture steel pipelines. And that's exactly why those emergency valves are designed to close just a little bit gradually, and why flow rates are controlled so carefully to stop a safety system from causing a whole different kind of disaster.
So the oil is loaded. It's safely in the tanks. How do we keep it that way for thousands of miles across the ocean? Well, the answer isn't just about what's containing the oil, but the atmosphere above the oil. And this brings us to what is, without a doubt, the single most important safety feature on any modern tanker.
The problem is really simple, and it's terrifying. The empty space above the oil in a tank, it's filled with flammable vapors. You mix that with oxygen from the air, and you have, quite literally, the perfect recipe for a bomb. So the engineering solution is just as elegant and simple. Get rid of the oxygen.
And they do this using something called the Inert Gas System, or IGS, and it's brilliant. It's basically recycling. The system takes the hot exhaust gas from the ship's own engines, which is naturally low in oxygen, cleans it, cools it, and then pumps it into the cargo tanks. The whole goal is to keep the oxygen level inside those tanks below 8%. Below that level, a fire simply can't start. No oxygen, no fire.
So this gas goes on quite a little journey. It's collected from the boiler, then it goes into a big scrubber tower where seawater cools it down and cleans out all the soot and sulfur. Then, powerful blowers push the clean gas through pipelines. And here's the most critical part. It passes through something called the deck seal. It's a simple, one-way water trap, but its job is absolutely crucial. It physically prevents any flammable gas from the cargo tanks from ever flowing backward into the engine room. Finally, the inert gas enters the tank, creating that safe, protective, non-explosive blanket over the oil.
So how do you actually get this safe gas into a tank that's already full of regular, unsafe air? Well, there are two main ways. The first is the displacement method. It's kind of like a piston. The heavier inert gas is pumped in at the bottom, and it gently pushes the lighter, oxygen-rich air out through the top. The other way is the dilution method. This one's more like turning on a giant fan. The inert gas is blasted in at high speed, mixing everything up until the whole atmosphere is safely below that magic 8% oxygen level.
All right, so the oil has been transported thousands of miles, it's been safely delivered, but the journey isn't over. You're left with these massive, empty, and dirty tanks, and engineers came up with a remarkably clever way to clean them.
It's called crude oil washing, or COW for short. And yeah, the name is literal. Instead of using water to clean the tanks, the system uses the cargo itself as the cleaning agent. High-pressure jets spray crude oil all over the tank walls, and that oil dissolves all the thick, waxy stuff left behind. That recovered oil is then pumped ashore with the rest of the cargo. It's so efficient and prevents so much pollution that it's actually mandatory under international law.
And the benefits are huge, right? You recover more of your product, and you drastically reduce water pollution. But, and this is a big but, the process creates its own serious hazards. I mean, you're spraying oil at high velocity, which creates static electricity and a ton of flammable mist. And this is exactly why crude oil washing can only ever be done in a tank that is fully protected by that inert gas system we just talked about.
And that really brings us to the main takeaway here. The loadicator, the alarms, the inert gas system, the crude oil washing, none of these are just isolated gadgets. They are a deeply interconnected web. Each system relies on the others to be safe. The whole thing is a triumphant proactive safety engineering. It's designed from the ground up to prevent a disaster, not just react to one. Which kind of leaves us with one last thought. We've seen the incredible complex lengths engineers go to just to manage the risks of moving oil. It really makes you wonder, doesn't it? If we can engineer this level of proactive, systems-based safety for an oil tanker, what other complex hazards in our everyday world are we completely overlooking?